I will start my presentation. The title is Projections of Future River Flood Inundation and Evaluation of Adaptation Measures in Toyama Prefecture, Japan. First, this is a presentation outline. First, background and objective. Rivers in Toyama Prefecture are known as rapid flow rivers in Japan. As a result, there is a lot of damage caused by erosions. Therefore, it is important to predict the danger areas. Also, Japan's temperature and precipitation are increasing due to global warming, and the frequency and magnitude of floods are increasing. So, flood risk assessment based on future climate is important. The next objective. The objective of study is adaptation and mitigation effects are also recognized proposed adaptation to global warming. Therefore, evaluates the effectiveness of adaptation measures in reducing the amount of flood inundation cost and comparing adaptation measures with mitigation considerations on several rivers. Next, research flow. First, rainfall runoff simulation. It is estimation of in channel discharge in the basin. Second, flood inundation simulations. It is calculation of inundation depths during flooding. Finally, flood damage cost. It is calculates the flood damage cost for direct damage based on the flood control and economic survey manual. Next, study area. We focused first-class rivers in Toyama Prefecture, Joganji River and Jinzu River, Sho River, Oyabe River, and Kure River. Next, flood inundation analysis in the future. It is a rainfall runoff model. I used a Kure Yamada model. It is a simulation of rainfall runoff on a single slope. Also, one-dimensional unsteady flow analysis was used to flood routing simulations for river channel. Next, setting reference coefficients. I used Ishikawa's research. High water beds is calculated through NDVI, which provides a satellite image of thriving vegetation, and low water edge channel is calculating marine stratigraphic conditions. The left figure is high water beds. The right figure is low water channel. Next, flood inundation simulations. We use two-dimensional flow two-dimensional unsteady flow equation was used to flood inundation simulation. Next, flood inundation simulations dataset. First, marine reference coefficients. I used image flow equations. This study uses elevation data with a resolution of 30 meters. The above equation is calculated from the house occupancy at the resolution of 30 meters. Next, deep breach point. First, a point at which the amount of damage cost is maximum, and deep breach starts at the peak water level. The rise of the deep breach was set as the rise of the river. Next, flood inundation simulation result, first and 4 Celsius. The left figure is fast, the right figure is 4 Celsius. First simulation, the Oyabe River, and on the right bank of the Jinzu River are high risk. And 4 Celsius, increased inundation area, especially on the right bank of Shogawa and left side of Jinzu River. Next, assessment of adaptation measures. 5 adaptation will be considered this study. First, great infrastructure. This is a comparison with adaptation measures with mitigating effects. Next, carbon dioxide emission limitations. First, vegetation management. The biomass, the vegetation can be biomass. Next, paddy field dam. This is no construction work required. Next, carbon dioxide absorption. First, green infrastructure. Stormwater management capacity can be improved. And forest conservation management. It can control flood flow runoff. First, vegetation management. This is vegetation management in a river. The left figure is before cutting the vegetation. The right figure is after cutting vegetation. We change the mining lumpens coefficient from high values to 0.03 after the vegetation cutting. Next, paddy field dam. This is a paddy field dam. We use the model of Chai-Toge. It is a one-dimensional paddy field dam model. Next, green infrastructure. Rainfall runoff simulation, where 10% of the city's area is represented as green infrastructure by classifying it as a mountain. Mountains increase, city is decrease. Next, deforestation. This study is deforestation. Runoff simulation, where 10% of the mountain area is represented as forest decline by classifying it as city. Mountain is decrease, city is increase. Next, flood inundation simulation results. This figure is difference of inundation depth. The left is vegetation management. The right figure is paddy field dam. In particular, vegetation management and paddy field dams appear most in the Oyabe River. Vegetation and paddy field dam. Next, green infrastructure. The left figure is no adaptation, green infrastructure, difference of inundation depth. The difference in inundation depth is around 0.2 meter, but the inundation area downstream is reduced. Next, deforestation. It is forest decline minus existing state equal difference. Left figure is no adaptation measures. Middle is forest decline. The right figure is difference of inundation depth. Inundation area extends downstream with a maximum inundation depth of more than 1 meter. Next, flood damage cost. This is flood inundation damage reduction rate only. Effectiveness of adaptation measures shown in Oyabe and Shou River and Jinzu rivers. Finally, summary. Oyabe River, vegetation management and paddy field dams and green infrastructure are extremely effective. Next, Shou River, Tokadamu and green infrastructure and forest conservation are effective. Jinzu River is steady forest conservation management, green infrastructure and vegetation management are effective. Next, Jonganji River, vegetation management is effective. Finally, Kure rivers. Currently, there are no effective adaptation measures, so drinking of haze embankments and irrigation dams and river channels also needs to be considered. Thank you.
Yeah, good afternoon. Thank you for the time. So, the regional climate change impact on flood inundation and evaluation of adaptation measures in Jakarta, Indonesia. Let me present myself. My name is Akbar Rizaldi. I came from Toyama Prefectural University. I'm a research student. Okay, this is content of my presentation. So we can see the background, proposed methodology, future condition, countermeasures, results, and discussion and conclusion. So the study area is for Jakarta area. You can see the black polygons. Jakarta, located in Ciliwung Basin, which located in Java Island, is in Indonesia. So Ciliwung River Basin, with a catchment area about 1,350 kilometers square, have several problems like rapid urbanization, trash clogging, insufficient river capacity, and also land subsidence. So Jakarta still experience flood every year. This is several flood events are noteworthy to assess. 2013, 2015, 2017, and 2020 is the latest noteworthy events of flood. And this is the land use conditions. So we can see that since 1983 to 2002 is very different. We can see the red area is urban area. So we can see the urban growth is very rapidly growing. This is the land subsidence. We got this from Abidin in 2011. He shown us the progress of the velocity of land subsidence for per year. So we can see this is the North Jakarta, which in coastal zone has experienced most the rapid land subsidence than others area. This is several human activity that make the capacity of river is decreasing. Trash clogging in Manggarai Gates and also illegal housing on the river bank. And this is came from the previous studies that show land use change and land subsidence increase the flood rates in future. So the brief summary of Jakarta has complex problem regarding flood. Future conditions such land subsidence, land use change, and climate change could make the flood condition deteriorate. And Jakarta needs innovative strategy to minimize the impact of flood in future. The purpose of this study is to assess alternatives to minimize the flood inundation area in future Jakarta under the future condition, including land subsidence, land use change, and climate change. So this methodology, we use rainfall runoff flood inundation model, which contains of three modules, that rainfall runoff modules by Kure and Yamada, and we do simulation to one-dimensional routing flood routing module. Then we simulate the flood inundation module to get two-dimensional flood condition. So before we try to assess the flood condition in various scenarios, we calibrate the condition by the 2013 events. So after we got a high index of Nash index and good agreement in correlation coefficients, so we can use this model and parameters to simulate the future condition. We also use slate model to project the future condition of land use map. So this is several variables we need to do simulation in slate model, so we can get the projected map of land use. So we also calculate the value, how can we know the risk of the future condition by flood by using EADC, expected annual damage cost. So we need to calculate the EADC, we need flood inundation map, land use map, so we know the affected area based on land use and head of water. Then we calculate the damage cost. So we have to calculate for each probability, then total it to get the EADC value. So this is several equation to calculate the damage cost and divide it into several kind of land use map. Then we also using the benefit cost ratio to see the efficiency of countermeasures that we will assess in this research. So the future condition, this is the projected land subsidence condition. This is we try to calculate, we try to model the future DEM of Jakarta to see the condition due to the land subsidence in 2050. Then this is the land use map in future Jakarta in 2050 by using the worst condition of SSP 3, and we can see that most of all the area of Ciliwung River Basin is urbanized. And we also using the global climate models, rainfall data to see the condition of the future. We use the ensemble GCMs, so we use the average value of this GCMS model, which affected by RCP 8.5. So we try to assess 4 countermeasures in our research. Countermeasures 1, CM1, CM2, CM3, CM4. CM1, we increase the river banks by 1 meter. And CM2, we increase the river bank 1 meter and dredge the river bed 1 meter. And CM3, by enlargement width of river 2 times. And CM4, make 4 ponds on the upstream of river. So the countermeasure which has good performance in minimizing or reducing the impact of flood will be analyzed the EADC and DCR value. So this is the figure of CM1. We increase 1 meter, CM2, we increase and we dredge the river bed. This is CM3, we enlarge the river width 2 times. And we put 4 ponds in 4 river in Ciliwung River Basin. Sorry. So the result, this is the result, the flood condition of each condition. This is without adaptations, CM1, CM2, CM3, CM4. Then next is we try to see the difference between the condition of flood between without adaptation and CM1. We can see difference area shown here are reduced. This is, we got the inundation area from 313 kilometer squares to 281.5 kilometer squares, and the inundation value also decreasing from 700 millions to 640.9 million. Then this is the CM2, and without countermeasure, we also can see the difference area here, and the inundation area also decreasing to 231.9, and the inundation volume also decreasing 500 million. Then this is CM3. This is a different area, reduced area. So then this is CM4. You can see the pond here. And this is how we can see the difference between each countermeasure, the effect of each countermeasure to the flood condition. So we can see the difference of colors and the area. This is CM1 without countermeasure. This is CM2 without countermeasure. CM3, CM4. And this is the summary of flood inundation. So we got the CM1 and CM2 show the highest area reduction of flood. Then we compare the 2 best of countermeasure on this research into the previous research. RRP, recharge retention ponds. RW is recharge wells. SWP, seawall protections. GI, green infrastructure. This conducted by Fajar in 2020, and we can see that the ADC value, still the RRP is the lowest EADC, which means that the RRP is the effective solution to reduce the flood condition in Jakarta in future. and then followed by CM2 and CM1, then the rest countermeasures. Then this is the benefit cost ratio. We got another point here that recharge wells show the highest benefit cost ratio, which means it's very less cost to apply these counter adaptation measures, and followed by RRT, then others. Then the conclusion is this study has projected the annihilation due to the impact of litter change, land subsidence, land use, and climate change. And several countermeasures have been evaluated quantitatively by combination of run of innovation and economic model. And two proposed countermeasures, CM1, CM2 in this study, provide a well for the reduction impact. Nevertheless, the cost is still too expensive than recharge and retention ponds and recharge wells. And the recharge wells is the most economic countermeasure with PCR is around 9. And even though the several structure countermeasures need high investment, the combination of them could solve flooding problem in Jakarta. Furthermore, a comprehensive benefit cost analysis may increase the feasibility study. So thank you for your attention.